So yeah, thanks for your time. That's all I have for this.
Hello, I'm Ricardo from Igalia. I'm going to talk about device-generated commands in Vulkan. This is a new extension that shipped a couple of weeks ago. I wrote CTS for it. I helped with the spec, and I worked with some actual heroes, some of them present in this room, that managed to get this implemented in a driver. Device-generated commands is an extension that allows apps to go one step further in GPU-driven rendering, because it makes it possible to write commands in a storage buffer from the GPU and later execute the contents of the buffer without needing to go through the CPU to record those commands like you normally do with by calling VK-CMD functions. It's like one step ahead of indirect draws and dispatches and one step behind work graphs. Getting away from Vulkan momentarily, if you want to store commands in the storage buffer, and there are many possible ways to do that. A naive approach we can think of is creating the buffer as you see in the slides, which is like we assign a number to each Vulkan command and store it in the buffer. And then depending on the command, more or less data follows. For example, let's take the sequence that is in the slides where you have one command to push constant, followed by a second command, which is a dispatch. So we can store a token number or a command ID or however you want to call it to represent or to indicate that push constants come. Then we follow this with metadata about the command, which is the section in green color, containing the layout, the stage flags, the offset and size of the push constants. And finally, depending on the size, we store the push constant data properly, which is the section that you can see there in blue, the first chunk in blue. And for the dispatch is similar, only that it doesn't need any metadata because we only want the dispatch dimensions. This is, okay, a naive idea. This is not how GPUs work. This is not even how Vulkan works. In Vulkan, we want to be able to process things in parallel. We want to provide as much information as possible beforehand. So this doesn't work. So in Vulkan, things are different. The buffer will not contain an arbitrary sequence of commands where you don't know which one comes next. So what we do is to create something that is called the indirect commands layout. And this is the main concept. So the layout is like a template for a short sequence of commands. And we create this layout using the tokens and the metadata that we saw color red and green in the previous slide. And we specify this layout in advance, and in the buffer, we only store the actual data for each command. And the result is that the buffer does not contain, let's call it the DGC buffer. It's divided into small chunks called sequences in the spec. And the buffer can contain many such sequences, but all of them have to follow this layout that we specify in advance. For example, we have the push constant values of a known size, followed by the dispatch dimension. So it is like that: push constant, dispatch, push constant, dispatch, push constant, dispatch. Okay. And the second thing Vulkan does is to severely limit the selection of available commands. You can't just start render passes or bind descriptor sets or do anything that you can do in a regular command buffer. So you can only do a few things, and they are all in this slide. There's general stuff like push constants, stuff related to graphics like draw commands and binding vertex and index buffers, and stuff to dispatch, compute, ray tracing work, and that's it basically. And moreover, to make things even simpler, each layout must have one token that dispatches work, and which is, draw, compute, or trace race, but you can only have one of those, and it must be the last one in the sequence. So that makes it even simpler. So something that's optional, not every implementation is going to support this, is being able to switch pipelines or shaders on the fly for each sequence. Summing up, in implementations that do allow you to do this, you have to create something called an indirect execution set, which is like groups or arrays of pipelines that are more or less identical in state, and basically they only differ in the shaders they include. And inside each set, each pipeline gets an index, and you can change the pipeline used for each of the sequences by first specifying the execution set in advance, second, using an execution set token, and then storing the pipeline index in the DGC buffer for each sequence. So a summary of how to use this for anyone trying to find how this works, reading the spec or interested in implementing this in a driver, is that, well, first you create the commands layout, and optionally you create the indirect execution set if you will switch pipelines and the driver allows you to do that. Then you get a rough idea of the maximum number of sequences that you will run in a single batch, and with that you create a DGC buffer. Then you query the required per-process buffer size, which is, the first time I mentioned that, is an auxiliary buffer that some implementations need to run this, and you allocate both buffers, the DGC buffer and the pre-process buffer. Then you follow by recording the regular command buffer normally, and you specify the state you will use for DGC in advance. This also probably includes some commands that dispatch work that fill the DGC buffer somehow. And finally, you dispatch the indirect work by calling BKCMD ExecuteIndirect commands. And note that you will need a barrier probably to synchronize the previous writes of the DGC buffer with indirect command reads. And you can also do explicit pre-processing, but I won't go into any detail here. And that's it. Thanks for watching. Thanks Valve for funding a big chunk of the work that involved in shipping this, and thanks anyone who contributed. That's it.